So far, we've looked at our outputs approaching positive and negative infinity and all of the subsequent little things that can happen as our denominator becomes 0. But just like having our output approach positive or negative infinity, our inputs could also approach positive or negative infinity. So we can ask, for instance, what the limit of 4 over x minus 3 is as x approaches infinity, or ask the limit of what 4 over x minus 3 is as x approaches negative infinity. So let's go ahead and do that. And I'm going to look at this graphically and numerically. I'll start with numerically. So numerically, what we're going to do is take my expression 4 over x minus 3. When we say x approaches infinity, we just mean that x is going to become, or we're going to plug in bigger and bigger values in for the x. So what we're going to end up doing is typing in bigger and bigger values. So how big should we start? It kind of depends on the problem, but I'll start with 100 in this problem and then go to 1,000 and then go to 10,000 and then go to 100,000 and then go to 1,000,000. If we didn't get big enough x's to see the pattern, then I would just go on further than that. Then I plug it into the expression 4 over x minus 3. If I plug in 100, I end up with about 0.041237, blah, blah, blah. If I input 1,000, I end up with 0.004. I might just round these to the couple of significant digits as I start. If I plug in 10,000, well, my calculator gave me scientific notation of 4.0012 times 10 to the negative fourth. The way the calculator does that, it says e negative 4. What that really is, it's a number which is 0.00040012. You get a lot of scientific notation in this when you do this numerically, because what's happening is these numbers are getting really, really, really small. 4 times 10 to the negative fifth, essentially. And then when you do the plugging in of 1,000,000, 4 times 10 to the negative sixth. Notice these numbers on the right here are getting closer and closer and closer to 0. Don't be fooled by these scientific notations. All that's saying is we're getting lots of zeros and then a 4. Even more zeros and a 4. And so as x is approaching infinity, my fraction is approaching 0. As we approach negative infinity, I'm going to plug in negative 100, negative 1,000, negative 10,000, and then negative 100,000. So as we do this, just type it in your calculator. You end up with negative 0.0388. when you plug in negative 100. When you plug in negative 1,000, you get negative 0.003988. When you plug in negative 10,000, then it becomes scientific notation, but negative 0.00039988. That's 3.998, negative 3.998 times 10 to the negative fourth. And then on the next one, you end up with scientific notation of negative 3.99988 times 10 to the negative fifth, which is a really, really small number. And so notice what's going to happen. I say small in absolute value. Notice what's happening here is we're getting closer and closer again to 0. So as my denominator gets really, really big and my numerator is staying 4, denominator getting really, really big is forcing the fraction to get closer to 0. When I say big, I mean big in absolute value. As the denominator gets really, really big in absolute value, the entire fraction becomes 0. So there's this little interplay between infinity and 0 here, and fractions. In particular, we see that if we have something like 4 over 0, we could get plus or minus infinity as my form. But if I have something like 4 divided by plus or minus infinity, I'm getting 0. Okay. So there's kind of this little exchange here between infinity and 0 on our forms. Now, when I say equal, I'm not saying that these two fractions are the same thing. In fact, neither of these fractions actually exist, right? Neither of these exist. But what I'm saying is, if the limit is having this 4 over 0 form, we saw we got plus or minus infinity. If the limit has 4 over plus or minus infinity, we saw that we got 0. Graphically, if you use Desmos or some other graphing calculator, let's say, to figure out how to graph, when we say we approach infinity, when we say our x value is approaching infinity, what we're saying is that our x value is moving towards the right. As our x value moves towards the right, you can see we're approaching the x-axis. So that means the y value is getting closer and closer and closer to 0 as you move to the right. And then on the left-hand side, as you approach infinity on the left-hand side, once again, you're getting closer and closer and closer to the x-axis. And therefore, you are approaching 0 as x goes to negative infinity. Positive, as x goes to positive infinity, this function approaches 0. And as x goes to negative infinity, this function approaches 0. So that finishes example 4. Just like the limit being infinity, we can also have an epsilon delta definition for the limit as x goes to infinity. It's slightly different. It means that given any epsilon greater than 0, there exists an m, a big enough m, such that if x is bigger than m, then the function minus L is less than epsilon. We can amend that to have x approach negative infinity instead of positive infinity. And all we're going to do is change the big M to an M less than 0, so it's negative, and then x less than m. So that means that you can get really, really, really close to the limit for a big enough value of x. Once again, we're not going to utilize the epsilon delta definition of the limit as x approaches infinity, but I did want to bring it to your attention. What I would like you to do is I would like you to either use graphical approaches or numerical approaches, or maybe some other approach you can think of to find the limit as x goes to infinity, and to find the limit as x goes to negative infinity of this rational function.